Welcome to the last part of lecture 16 for Math 2R03. Now, in the last part, I just showed you that the number for distinct eigenvalues, we get distinct eigenvectors, and those eigenvectors must be linearly independent. Now, the nice thing about this is we can actually prove that there's going to be a cap on the number of distinct eigenvalues. In particular, if we know that the dimension of our vector space is n, then any linear operator has at most n distinct eigenvalues. Now, we would have proved this in Math 1B03, or kind of talked about why this is true in Math 1B03 by talking about using the characteristic polynomial and looking at determinants. But we don't have any of that, any of those tools available to us because we haven't discussed them. But we can still actually prove that every linear operator has at most n distinct eigenvalues using the previous result. And let me just show you, it's only a 2-3 line proof. Right? Suppose that you looked at the distinct eigenvalues, lambda 1 up to lambda m, they're distinct eigenvalues, and you had its corresponding eigenvectors, v1 up to vm. Well, we know that since v1 up to vm are linearly independent, we must have m is less than or equal to n, which is equal to the dimension of v, right? Because in an n-dimensional vector space, you could have at most n linear independent things, right? So what we have here is we don't know what this number m is, but m always has to be less than or equal to n. So in fact, that's the proof. Okay, so you don't need to do determinants or characteristic polynomials to have a bound on the number of distinct eigenvalues of a linear operator. Okay, so speaking of Math 1B03, how do you find some of these eigenvalues? Okay, so here's a kind of a very simple question here. Let's say we have a linear operator from R2, so it's a linear map from R2 to itself. It's given by taking the pair xy and mapping it to 3x, 4y. And you want to find the eigenvalues of this linear operator. Now in 1B03, we use determinants, and we don't have these tools, okay, in this book. Okay, so we're kind of giving ourselves we're making things more difficult for ourselves that we don't have the determinants. Now, when you're doing your homework and you're working out problems, you can use the fact that we have the determinants to work out these values, okay? It's not like anything that we learned in 1B03 can't be used. But let's say that you haven't seen how we would have done this in 1B03. How are you going to find the eigenvalues? Okay, it's actually a little bit tricky to do this because you have to use, if you're only using the definition, let's think about how you would do it that way. So you want to find a lambda such that when you look at any vector txy, so you get 3x, 4y, it would be the same thing as getting lambda x comma y. Right? And you can rewrite this as lambda x, lambda y. So what we have is, we have that 3x is equal to lambda x, and we need that 4y is equal to lambda y. Okay, so we have to be able to find x's and y's to solve this system of equations. Okay, so here's kind of the only solutions to these equations, right? So the only solutions would be take lambda equal to 3 and y is equal to 0 and x arbitrary. So that's one solution. Another solution would be take lambda is equal to 4 and x equal to 0 and y arbitrary. Kind of these are our only choices in order to make both of these equations true. Okay, and we can do a quick check that this is true. So our check would be, let's look at 2, 3x, 0. It gets sent to, x is arbitrary. So 2x0 gets sent to 3x comma 0, which is the same thing as 3x0. Okay, and if I take t evaluated at 0y, it gets sent to 0, 4y, which is the same thing as 4 times the thing that you started with. Okay, so these are definitely eigenvalues. Okay, 3 and 4 are eigenvalues, and we also note 1, 0 is an not an eigenvalue, it's an eigenvector of 3. Okay. Okay, and we also have 0, 1 is an eigenvector of 4. Okay, so we're almost done this part here. Let me just give you one more example of looking at a linear operator and trying to find its eigenvalues. So this one's a little bit more interesting. We have that D is the differential operator, which we're looking at all polynomials with coefficients in R. And what this operator does is it takes a polynomial and maps it to its derivative. Okay, so map P to its derivative. Okay, so this is a little bit different operator. We wouldn't have seen this in Math 1B03. And lambda is an eigenvalue of D if and only if when you take the derivative, right? So you take your function P, you take the derivative, so that's P prime, it has to be equal to the scalar multiple of the function you started with. Now, if you sit down and think about this for a second, and you remember what you know from calculus and polynomials, you can't actually do this very often, right? If the degree of your polynomial is greater than or equal to 1, then the degree of your derivative goes down by 1, okay? Or it might actually go down, yeah, it will go down by 1. So you actually will never have a solution, okay? Then no solution to P prime, oops, can't see the prime there, no solution to P prime is equal to lambda prime, lambda times P, since both sides have different degree. Okay. On the other hand, if we look at a polynomial of degree 0, well then we know that the polynomial P has to be equal to some constant C, or some constant C inside of my field F. Okay, and now it is actually possible to satisfy this equation here, right? Because then the derivative of P is 0, and the derivative of P, which is 0, is the same thing as 0 times the function that you started with. So we have that lambda equals 0 is an eigenvalue of the differential operator D. Okay, and so that's kind of an interesting example of where we're seeing eigenvalues of linear operators that we wouldn't have seen in Math 1B03. So let me just kind of wrap up here by kind of just doing a quick summary of the key ideas from today's lecture. So we learned about invariant subspaces. These ideas are going to come up over and over again in this chapter. We learned about eigenvalues and eigenvectors in a much more general setting as when we're looking at linear operators. So I hope you enjoyed this lecture, and we'll continue our discussion of eigenvalues and eigenvectors in the next part. Okay. Until lecture 17, have a great day.